Hello, and welcome to the presentation, The Role of X-Ray Computed Tomography in Additive Manufacturing. My name is Herminso Villarraga Gomez, and I currently work for Zeiss Industrial Metrology out of the office located at Wixon, Michigan. Let me start with this question. Do you recognize this process? Too bad that I cannot hear your answers in a pre-recorded video. So let me help you. It is subtractive manufacturing, a very old technology dating back to the prehistoric period of the Stone Age. What about this one? Do you recognize this process? That is additive manufacturing, which, as opposed to subtracting manufacturing, is created by adding material layer by layer. This is a popular technology that people are using for many manufacturing applications, including 3D printed houses that will potentially lead to a revolution in the real estate market. And to give you some more traditional applications for manufacturing medical parts, for example, there are several pictures here that are taken from the Journal of Quality Technology, which include applications of orthopedic medical implants. But there are several challenges in quality assessment of additive manufactured parts. First, they can be made in complex free-form shapes, which are great in terms of engineering, giving almost unlimited degrees of freedom for design, but this creates technology challenges in terms of quality inspection, given that part features might not be perfect circles, not perfect spheres, or planes that are used by traditional measurement systems as reference to construct geometrical characteristics. This will make it difficult for those measurement systems to create a measurement plan. Second, additive manufactured parts might have internal features that cannot be seen by an optical system or measured with a tactile measurement machine, unless there is an opening to get inside, but it will be challenging to get accurate measurements that way. Third, the additive manufacturing surfaces generally have a high degree of surface roughness that can make it challenging to measure with tactile measurement machines. And fourth, it is not surprising that additive manufactured parts might have unmelted powders, particles in the inside, or some level of porosity that is difficult to assess without cutting or slicing the final product, unless you use X-ray technologies. There are actually several solutions for non-destructive inspection of additive manufactured parts. For example, white light interferometry, which has very high resolution capabilities, but is limited to scanning the surface. There is also adding current techniques and ultrasonic testing, and they can certainly penetrate the part, but have limitations in the achievable measurement resolution. So far as now, the technology that can reconstruct the full volume of a part, including external and internal surfaces, is the 3D X-ray computed tomography. And it can give you image spatial resolutions down to nanometers. And from the several types of X-ray imaging technologies that can provide resolution ranging from millimeters to nanometers or submicron level, most of the industrial quality inspection solutions with X-rays, specifically for dimensional metrology, have been limited to micro-CT or macro-CT technologies. Not so much has been done in industrial dimensional inspection with techniques that reach submicron spatial resolution until recently. We launched a metrology extension for Zeiss X-ray microscopes last year to address this problem. And it is worth noting that from several interlaboratory studies that compare micro-CT technologies with traditional coordinate measurement systems, or tactile CMMs, the spread of uncertainty values being associated with X-ray CT measurements covers a range that goes from around 1 micron to more than 50 microns. In the traditional micro-CT world, the main approach is to use projection-based systems that are basically composed of an X-ray source and a detector and a rotational stage to place the part. But the imaging resolutions of such systems is limited to something around 2 microns, in the best case scenario when optimal settings are used for measurement. But there is a possibility to improve things and deliver submicron resolution capabilities if we use 3D X-ray microscopes. The main difference of the so-called 3D X-ray microscopes as compared to the traditional projection-based micro-CT systems is that they include a set of lenses that are optical magnification capabilities additional to the geometrical magnification. This allows achieving submicron resolution capabilities. With traditional projection-based X-ray CT systems, it's difficult to achieve that. This is not a problem for the 3D X-ray microscopes we design at size because of what we call resolution at a distance, which preserve high-resolution data reconstruction even for larger samples, but by combining geometrical magnification with optical magnification. This is one example that illustrates quality inspection of parts made by additive manufacturing techniques. Without destroying the part, we can inspect at high resolution the structural integrity of the internal cavities, check for internal defects such as porosity or impurity inclusions in the powder material, and do measurements of surface roughness. Here is one more example of a 3D printed lattice structure made of Inconel. You see data for two different scans, one at 8 micrometers voxel size and a small regions of interest scan at 3.5 microns. In the cross-sectional images, you can see several interesting details of the build, such as internal porosity, and also you can appreciate how the surface roughness around the joints features in the lattice structure looks like. This is a small portion of an aluminum gear wheel made by additive manufacturing. This has been scanned with 3 microns voxel resolution, which allows the inspection of porosity, unmelted powder particles in the finished part, and the detection of unexpected particle inclusions in the powder. All sorts of defects that might affect the functional performance of the part can be detected without destroying the part with X-ray computed tomography, with high-resolution imaging capabilities, if we use the so-called 3D X-ray microscopes. Inspecting the powder before building the part is also important for additive manufacturing. And this is demonstrated here by the CT scan of a portion of 3D printing material. The more uniform the powder is, the more consistent is the build. But as you can see from the picture, the morphological characteristics of powder particles can be very diverse. They are non-uniform and can come in diverse shapes that are non-spherical. They might come in a broad range of particle sizes, which can be a problem for melting purposes. In fact, there are some particles that already contain porosity within themselves, which could explode during the 3D printing process and even degenerate in defects such as cracks in the manufactured part. For the example of this spinal truss implant, we can take the finished part after the manufacturing process, then scan the part with X-ray CT to generate a 3D volume reconstruction. Use a surface determination software to generate a mesh of the part, all the internal and external surfaces, and then apply simulation-based loads to such surface data. You can do similar simulation out of the original CAD model or part design geometry, and then compare the results from both simulations as manufactured versus as designed. Here is a clear comparison of the two results, showing some differences of the geometrical deformation of the part when the force load starts going above 20 newtons, although the trend is similar between the two, as manufactured versus as designed. But this example illustrates how from the CT scan of a final product, it can be used to verify predictions from simulations of the model design. This is how we make the invisible visible with X-rays. And by now, you probably have a pretty good idea of what the role of 3D X-ray computed tomography is in terms of quality assessment of additive manufactured parts. There are different X-ray CT technologies that can help you with the assessment of additive manufactured parts, including the so-called 3D X-ray microscopes, which are part of a larger set of multi-scale correlative microscopy tools, including microscopes capable of delivering resolutions down to half a nanometer, with a helium ion microscope, for example. With 3D X-ray microscopes, we can go down to spatial resolutions in the order of 50 nanometers and correlate the non-destructive images with data from other microscopes. With this, I would like to thank you for coming to my presentation. If you have any questions, I'll be happy to answer. Please send me an email to herminso.gomez@site.com.